So you are not a fish, but there might be more fish features about you than you realized. So when you started as an early embryo, your eyeballs were actually on the side of your head, and then they migrated towards the center, and they pushed your nose and they pushed your mouth, and that little lip right between your nose and your mouth, that's a remnant of that. So it might not be obvious that you're a fish, but every time you feel that, remember, your fish ancestors are not that far away. Now, some of the things that make us similar to fish are obvious on our face, and other things are deeper in our DNA. And I was a research technician at the University of Southern California, and there I was working for the Stem Cell and Regenerative Medicine Institute. And guess what they were using? Fish. Because fish are a really good model for understanding how basic developmental processes work. Their embryos are clear and transparent, and they're vertebrates. Turns out studying vertebrates is pretty useful for some stuff. They're closer to humans. Get into that later. But fish have, some unique features about them that are similar to humans, but slightly different than humans. So take, for example, the synovial joint in a fish. A synovial joint, if you injure it the right way, a fish will become arthritic. We become arthritic. However, in fish, you can actually reactivate part of that tissue and you resolve the arthritis. That might be kind of useful to do in humans. In a fish, you can actually do a little tiny, very careful surgery. It's kind of difficult. They're quite small. You can cut a tiny bit of the heart. The heart will regenerate. Sure, it'd be useful to know how that happens. One of the projects I worked on was we were able to resect a portion of the jaw in a fish, cut out a piece of the bone, and the bone would actually regenerate. And what was really interesting is it would regenerate not the way it originally formed. A small cartilage bridge would come across between the two joints, and then that joint would fuse, and then it would solidify and turn into bone. So these sort of things I'm telling you about, they're not, we're not going to be putting fish hearts in you anytime soon, or fish bones, but it's more like the basic biology. How do those fundamental phenomena happen? That is actually could be pretty useful. I recently injured my leg, which is why I was very slow to get up here. And so this event was a good opportunity. I did a quick Google search, and so I Googled fish ligament evolution. And it turns out no one studies that. So like if you're looking for like a hot topic to get into, I'm thinking like fish ACL reconstructive surgery. It could be like a really hot topic in the future. So fish hold these secrets, these secrets around biology that are not always obvious. And I also have a secret. My secret is I don't study fish. And so I apologized to Melissa, but I was like, hey, can I still come tell a story, even if it's like sort of fish adjacent? And she was like, that's cool, still come. So I actually work on a group of animals called hemichordates. They are these strange animals. They're worms. They are more closely related to sea urchins and sea cucumbers. They look like worms. They're unfortunately very phallic, so I apologize on behalf of the phylum. And so what makes hemichordates really useful in the way they're positioned to humans actually has to do with their butt. Scientists, they try to cover up stuff, and I'm trying to uncover some of that. Just like a hemichordate, you as an embryo, you formed your butt first. You are butt-first animals. There are mouth-first animals. Those are the protostomes. There are deuterostomes, which is mouth second, but that's really saying butt first. You can think about your closest relatives being butt-first animals. But hemichordates are really, really useful, other than just having butts. So what's useful about hemichordates? Well, they have like some features that are kind of like humans, and then some features that are really not like humans. So for instance, a hemichordate has three parts of its body. It has its proboscis, its collar, and its trunk. How are those regions of the body established? That's a thing developmental biologists spend a lot of time thinking about. So it turns out the same way the hemichordate makes the proboscis region is the same way the vertebrate brain is patterned. In terms of the forebrain, that's proboscis region. Collar, that's midbrain region. Posterior, that's hindbrain region. Now, obviously, the output of that is not the same. The hemichordate is not having the same thoughts that you are having. It's probably having very few thoughts. But in terms of deep genetic similarities, that's where the conservation is. So these networks sort of get played out in lots of different ways. And that's sort of where my interest in research is like, when do these things like start to break down, and when do they hold true? Like, what actual similarities can you draw? Obviously, outputs are different, but inputs are similar. Where does that stay the same? Where is it different? So for my research, as a marine biologist, I get to sometimes go to really beautiful places, and other times I go to less beautiful places. So a lot of my classmates, they go out to Baja, or they go to the coral reefs. I spend my time on a mud flat. It's very exciting. It's very muddy. Currently, so you have to dig these worms out of the mud, and the mud's couple meters deep, and you stick your shovel in there, and you hopefully get a worm. Now the problem with this would normally be fine, but it turns out their burrows often get occupied by other animals. So half the time you're just digging out other stuff. Sometimes fish. I never thought I'd be so annoyed to find fish. What are fish doing in my worm burrows? So you're out there digging them out of the mud. You got to lift this chunk of mud that's quite thick out of the mud. You break it apart, find the worm, take it back to lab, do all the stuff. That would work fine, except sometimes in your PhD, you don't find the animals. And that always provides an interesting phenomenon. I was out there on my first collecting trip ever as a new PhD student. I had been shown the site before, but I went out there on my own, didn't find a single worm. The next chance for a low tide was at 3:30 in the morning. So it's down in Morro Bay. It's a little bit of a drive from Hopkins. I get in my car around midnight, drive down to Morro Bay. So I'm just walking back and forth across this mud flat. I got my headlamp on. I got my shovel. I look like a crazy person. But I indeed did find the worms. It was probably the happiest I've ever been. The second happiest I've ever been. So found the worms, took them back to lab, was able to do my experiments. And what I'm doing with these animals is asking questions about how do they build their body. Because this hemichordate is really interesting in the fact that it has a larval body and an adult body. So things like fish, things like humans, we're kind of boring. We just go from embryo to adult. That's not interesting. What's interesting is animals that build one body that then changes into something else. That happens, to most all animals on the planet, except developmental biologists are like, that's kind of hard, that costs too much money, it takes too long, we don't want to study those things. But I'd say there's too much remaining interesting biology to be solved. And I would also say sometimes it takes a worm to hook a fish to learn more about humans.